Hi students, let's get started with section 4.4, which is on polynomials. In this lesson, we are going to classify a polynomial as a monomial, binomial, or trinomial. We're going to find the degree of a polynomial, and we're going to evaluate a polynomial and polynomial functions. One important thing to know is that terms are separated by a plus and a minus sign. A term with the highest power is called a leading term, and its corresponding coefficient is called a leading coefficient. The degree of a polynomial is determined by the exponents on the variables. Let's fill out the chart below. So here I'm giving you an example of a polynomial, negative x to the fourth minus 5x minus 8. The degree is for this polynomial, since we're dealing with one variable, it will be the highest exponent. So our degree for this particular polynomial is 4. Our leading coefficient is negative 1, since negative 1 corresponds to the variable with the highest exponent. And the number of terms we have 1, 2, 3. Notice that these terms are separated by a minus sign. So we have 3 terms. Next, we have 1, 2, 3, 3 terms again. But what is the degree? Which term has the highest exponent? Well, it will be this term, because 5 is higher than 4 or 3. So our degree here is 5. And since the leading coefficient is 5 as well, we're going to write 5 also under leading coefficient. The next polynomial, or constant as we should call it, the next constant, 10, is similar to 10 times x to the 0. We already know that x to the 0 equals 1, so 10 times 1 is 10. Therefore, our degree is 0, because 10 is equivalent to 10x to the 0, and the exponent we see here is 0. We're going to say 10 is our leading coefficient, is our constant, and we only have one term. The next example, I want you to determine a polynomial. I want you to come up with a polynomial or create your own polynomial that has a degree of 2, that has a leading coefficient of 7, and I want your polynomial to only have 2 terms. So what I want you to do is pause the video for a couple of minutes and write a polynomial that is indicative of those 3 things. Check yourself. Does it have a degree of 2? Does it have a leading coefficient of 7? And does your polynomial have 2 terms? So pause the video now and work on that. Okay, so I'm going to give an example. My example would be, since I have to have a leading coefficient of 7, it would be 7, and my degree has to be 2. So I'm going to put 7x squared, but that will only be one term, which is a monomial. I'm going to add a term to it. For example, I could put minus 2x, so that my polynomial has 2 terms in all. Now let's talk about 1 term, 2 terms, 3 terms. When you have 1 term, it's called a monomial. So these are some examples of monomials. 1 term. Then 2 terms are called binomials. So here in the middle column we have examples of binomials because there are 2 terms. And then 3 terms are called trinomials. And this last column, you have examples of polynomials with 3 terms. Now, this next page is a little different. What's different from these examples, these here, than these examples here? Well, the difference is that we had one variable in these examples, but now we're switching it up, right? So notice we have 2 or 3 variables. So the rules change a little bit for the degree. So when you have a polynomial that has more than one variable, then the degree, and this is a monomial, by the way, because notice there are no plus or minus signs in between. So this is acting as one unit. So the degree of a monomial with several variables is the sum of the exponents. Sum of the exponents on these variables. So notice here we have a 4, a 2, and an 8. Sum in math implies what? Sum. Well, total, right? Addition. So what we're going to do is add 4 plus 2 plus 8 to get the degree. So that would be 14 if we add 4 plus 2 plus 8. Our leading coefficient, what would be considered to be in front of x to the 4th, y to the 2nd, z to the 8th? Let's put 1. And we only have one term for this case. So this was an example of a monomial. Now next, we have 2 terms, right? So I'm going to go ahead and put 2. That's an example of a binomial. Well, it's a little different. This is not a monomial this time, but we do need to still sum up the exponents in each term to determine what's the degree. So for example, we have a sum of 7 here, and we have a sum of 6 here. Now, which is the highest? The highest is 7, right? So our degree here is 7, and our leading coefficient is 15 because 15 is associated with the term with the highest sum. Now let's move on to the next. We have 1, 2, 3. 3 terms here. We're going to call it a trinomial. Now, what is the degree of this polynomial? Well, you have to add the exponents and figure out which term has the highest sum. So here, what most people would do is they would skip the fact that m is there and that m has an exponent of 1. So that sum would be 7, then we have 4, and then we have 6. So 7 is the degree of this last polynomial here. And what coefficient is associated with that term? It is 16. So let's move on now to another concept in this section, which is called evaluating. So to evaluate simply means to make a substitution. All right. So you're going to replace the variable with something else. And I decided to discuss evaluating functions. Because if you understand how to evaluate functions, you understand how to evaluate everything else. Now here's a function, f of x. So we pronounce this f of x. It does not mean f times x. This is notation for what we call a function. We normally write an f for function. However, this could be G, this could be any letter of the alphabet. But you will mostly see F or G. F of x equals 3x minus 4. And we're going to evaluate this function for x equals 5. What does it mean? All we're doing is replacing the x with a 5. It's pretty simple. So notice that we rewrite the function, and wherever there is an x, we replace it with a 5. I would like you to always put a parenthesis anytime you are evaluating a function. Okay? That's going to be very, very helpful. So for example, where we have f of 5, that's already includes a parenthesis. That's already including a parenthesis because here there was already a parenthesis, right? But on the right side of the equal, we put 3 parentheses 5 close parenthesis minus 4. That indicates multiplication. So 3 times 5 is 15. Then we have minus 4. Next, we rewrite the left side, f of 5, because there is nothing to compute on the left side. It just represents a function saying that we are inputting 5 into this function. 3 times 5 is 15 minus 4, which is 11. So f of 5 equals 11. What does it mean? When we input 5, so input, 5 is our input, and our output is 11. So now let's try evaluating f of x, the same function, when x equals negative 3. So we have f of something equals 3 times something minus 4. So again, we are replacing the x with something else. So we're going to replace it with a negative 3. We're going to rewrite the left side. There's nothing to compute when it's a function. 3 times negative 3, negative 9 minus 4. But the right side, as you can see, we can compute it pretty easily. Negative 9 minus 4 is negative 13. So what is our input? Negative 3 is correct. What is our output? Negative 13 is correct. And with this information, we could easily graph this information because all we need are x's and y's, right? Coordinates. So this, for example, if I wanted to plot this, that coordinate would be negative 3, negative 13, because negative 3 represents the x and negative 13 represents the y. Let's move on to the next example. We're going to evaluate the same function, but when x equals 0. So again, always just, as a rule of thumb, just go ahead and put a parenthesis wherever you're replacing your variable with something. So we're going to replace our x's with zeros. So we have f of 0 equals 0 minus 4, since 3 times 0 is 0. So we have f of 0 equals negative 4, since 0 minus 4 is negative 4. Now, make sure that you understand your integer rules. Next, we have f of something equals 3 times something again minus 4. What are we replacing? We are replacing the x with a w. Simple as that. So if I put w in these parentheses, you're simply going to get f of w equals 3w minus 4. Since these are not like terms, we cannot go any further. Next, we have f of what? So let's walk through this together. What are we putting inside of this parenthesis? We are putting 2w inside of the parenthesis. 3 times 2w again, minus 4. So F of 2w equals what? 6w minus 4. Again, these are not like terms, so we cannot do anything to that 6w minus 4. That is the answer. Next, F of what? What should we put inside of this parenthesis? W plus 1 is correct. Then we're going to rewrite our 3. Let me put that in black. We're going to rewrite 3. And we're going to replace our x with w plus 1. Again, very good rule of thumb to put that in parentheses, because now notice we have to distribute. So we have f of w plus 1 equals 3w plus 3, since 3 times 1 is 3. Then don't forget the minus 4. So f of w plus 1 equals 3w minus 1. Why? Because actually 3 minus 4 are like terms, right? They're just plain constants that we can work out. Now let's change up the function to f of t equals negative 3t squared plus t minus 1. Notice we changed the variable to t instead. Still works the same. It's a variable and we're replacing it with something else. What are we replacing it with this time? Notice that the left side has already been filled in for you. So x is being replaced by a 0. So on the right side, we're going to replace all of the t's or the x's, right? In this case, it's a t. We're going to replace the t's with 0. So here we have negative 3 times 0, because 0 squared is 0, plus another 0 minus 1. So really we have 0 minus 1, which is negative 1. Negative 1 is our answer for that one. Now let's try f of negative 1. T is being replaced by negative 1. So negative 3 times negative 1 squared plus another negative 1 minus 1. So here we have negative 3. Always must follow PEMDAS. Please excuse my dear Aunt Sally. Meaning, we need to do parentheses and exponents first before we decide to multiply. So negative 3 times positive 1, because, let me write all of this in black, because negative 1 squared is negative 1 times negative 1, which is positive 1. And let's rewrite everything else. So that's negative 3 minus 1 minus 1, which is negative 5. Next, we have f of negative 2 equals negative 3 times negative 2 squared plus a negative 2 minus 1. This would be a good time for you to pause the video and complete this on your own. So we have negative 3 times positive 4 minus 2 minus 1, which is negative 12 minus 2 minus 1, which is negative 15. Let's move on to evaluating this last function here. G of t equals negative. Do you know what these symbols mean? Absolute value. Okay, absolute value is basically means the distance from 0 on the number line. But what we're going to do, we're going to replace the t's, because we notice we're dealing with t's, with 0 here. So negative absolute value 0 plus 2 close the absolute value symbol, plus 3. So we have negative, and what's the absolute value of 2? Well, it's the absolute value of 2 is 2, but notice there's a negative on the outside that you have to drop down, okay? Now the absolute value of 2 is 2, so that only corresponds to what's on the inside of these vertical lines here, not on the outside. So yes, the absolute value of 2 is 2. That's why we drop 2 down. But there's a negative on the outside of it, so you have to drop that negative down as well. So what is negative 2 plus 3? Positive 1 is correct. G of negative 5. So we have negative. So notice when I say G of negative 5, we're referring to the G function, right? If I said f of something, then we have to figure out what f function that that problem was pertaining to. But here we're talking about this function above the G function. We have negative absolute value negative 5 plus 2, close it, and then we have plus 3. So we have negative on the outside, absolute value. Let's go ahead and compute what's on the inside of the absolute value. So that's negative 5 plus 2, which is negative 3. Then we write down plus 3. I'm going to drop down the first negative is on the outside. But what is on the inside of the absolute value? There's a negative on the inside. What's the distance of negative 3 from 0 on the number line? It's just 3. Right? Distance is always positive. That's why we always say to make absolute value numbers positive, because we're talking about distance. So lastly, let's plug in positive 7 into our function. So we have negative absolute value of 7 plus 2, close it, plus 3. So this will be a good time for you to determine if you understand the material by pausing the video, and once you're done, playing again. So we have negative, then we have absolute value of 9 plus 3. We have equals negative 9. What's the absolute value of 9? Just 9, but we had to drop the negative that was in the front, plus 3. So the final answer is negative 6. Let's move on to graphing. Hopefully you are already a little familiar with graphing from high school, but let's go through graphing a linear function. So we have this first one is a linear function, and I know that because our x is to the first power. So if your degree is 1, then you have a linear function. If your degree was 2, then you would have a quadratic function. If your degree was 3, you would have a cubic function. So I know that this would be a straight line once I graph. Alright, so I'm going to create a chart. So I'm going to erase this and create a chart. So what we're going to do, we're basically evaluating this function, but we're going to create a chart out of it. We're going to plug in some x's. We make up the x's, and this is sort of like a T-chart that you're used to. We're going to plug in the x's. For example, I like to normally go with negative 1, 0, and 1. So f of x equals, this is our function here. What we're going to do is plug in our numbers like negative 1. And I want you to tell me, what do you get for your f of x? F of x is your output or your y. Your x is your input. Your y is your output. So what you get is, notice, negative 3 minus 4. which is -7. So if I wanted to write this as a point, I would write it like this. Normally I would write x, y, but since f of x is the same as y, we write now x, f of x. Our point will be, what is x? -1, because that was our input. And what is our y? Our y is -7. So our point is -1, -7. Next, plug in 0. 3 times 0 minus 4. So what is 3 times 0 minus 4? That will be 0 minus 4, which is -4. And our corresponding point is 0, -4. When we plug in 1, we have 3 times 1 minus 4. 3 minus 4 is -1. So what is our corresponding point? It is 1, -1. Now we're going to plot our points. Now let's plot the points. So let's first plot the point -1, -7. So we're here in the center. That's called our origin. We're going to move 1 unit to the left. And then we're going to move 1 unit, 7 units down. So 1, 2, 3, 4, 5, 6, 7. And we're going to plot our point there. That's -1, -7. Our next point is 0, -4. So we're in the center. That 0 represents the x-axis and the -4 represents the y-axis. So we're going to go down 4 units. 1, 2, 3, 4. That's 0, -4. And now we're going to plot 1, -1. From our origin, we're going to move to the right 1 unit. And then we're going to move down 1 unit. That is 1, -1. Notice we have a straight line. So you'll use a straight edge, anything with a straight edge, to draw your straight line. So I'm just going to draw it as straight as possible here, but I want you to use a straight edge. Notice that this line is going to positive infinity on your right side. It's continuously going to your right, which is to positive infinity, and on the left is going to negative infinity on the x-axis. So on the x-axis on the right is going to positive infinity and it's going to negative infinity on the left side. So our domain pertains to the x's. So our domain is from negative infinity to positive infinity. Our range pertains to the y's. So our range will also be negative infinity to positive infinity, because if you look on the y-axis, this line is going continuously down this y-axis all the way to negative infinity, and it's continuously rising to positive infinity. Let's move on to the next function. The next function is f of x equals -2x plus 1. So we're going to choose the same numbers for our x, -1, 0, and 1. And we're going to plug those numbers in to our function. F of x equals -2x plus 1. Let's try -1 first. F of -1 equals -2 times -1 plus 1. What would be our output for that? Our output would be 2 plus 1, which is 3. Therefore, our corresponding point would be -1, 3. Now let's plug in 0. If we plug in 0, we get f of 0 equals negative 2 times 0 plus 1, which is 0 plus 1, which is 1. So our corresponding point is 0, 1. Next, let's plug in 1. We write f of 1 equals negative 2 times 1 plus 1. Negative 2 times 1 plus 1 is negative 2 plus 1, which is negative 1. So our corresponding point is 1, negative 1. So let's plot our 3 points on the graph. So let's first plot negative 1, 3. From the origin, we will move to the left 1 unit, and we will move up 3 units. 1, 2, 3. For 0, 1, we'll start at the origin again, but we'll move up 1 unit. That's 0, 1. And for 1, negative 1, from the origin, we'll move to the right 1 unit, and then we'll move down 1 unit. That's 1, negative 1. Then we connect our dots using a straight edge. Again, our domain is from negative infinity to positive infinity, because on our x-axis, this side is going continuously this way, which is negative infinity, and the right side is continuously going on the right side, which is positive infinity. So our domain is negative infinity to positive infinity. Our range, if we look from the bottom to the top, notice that on our y-axis, this is going this direction, which is negative infinity all the way to positive infinity. And with infinity symbols, we always use a parenthesis, no matter what. Our last 2 examples for this section are f of x equals x squared. Our last 2 problems for this section are f of x equals x squared and f of x equals x cubed. Notice that the degree of this function is not 1. So it is not a linear function. It's actually a quadratic function. So we will not end up having a straight line anymore because of the degree, and the shape of the points will end up looking like a U. So let's plug in some points, but plug in some numbers for x, but we want to plug in more numbers for x to have a more accurate picture of what this function looks like. So we're going to use some additional x values. Let's start with negative 2, negative 1, 0, 1, and 2. So if we plug in negative 2 into this function, we would get negative 2 squared, which equals a positive 4. And the corresponding point would be negative 2, 4. Next, let's plug in negative 1. Plug in negative 1, we get negative 1 squared, which is positive 1. So the corresponding point is negative 1, 1. Plug in 0, we will get 0 squared. So we'll have 0, 0. Plug in positive 1, we'll get 1 squared, which is 1, 1. Plug in 2, we will get 2 squared, which is 4. So the corresponding point is 2, 4. Let's plot those numbers here. So we have negative 2, 4, to the left 2, up 4, 1, 2, 3, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4 here. So notice this shape is definitely not a line. It is a U-shaped figure. So our range will be totally different from the previous examples. Our domain, notice this left side is still going continuously to the left. So we still have negative infinity to positive infinity if you look at the x-axis. However, if you look at the y, the bottommost point is this point, the bottommost point. So we're looking at the y-axis at this point for the range. So the bottommost point is 0. And we're going to put a bracket there because it is actually including the 0. It's touching the 0. And if we look at the topmost point, notice that the top is continuously going to positive infinity. Lastly, we have the function f of x equals x cubed. So if we draw a table again, and we use -2, -1, 0, 1, and 2, I'm going to take a shortcut. I'm just going to put y or f of x here. We plug in -2, we get -2 cubed, which is -8. Plug in -1, we'll get -1 because -1 cubed is -1. Plug in 0, we get a 0. Plug in 1, we get 1. And plug in +2, we will get +8. So let's plot those points. So -2 to the left, 2 units, down 8. 1, 2, 3, 4, 5, 6, 7, 8. -1, 1 is here. 0, 0 is here. 1, 1 is here. And 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Notice this shape is not a line as well. It kind of curves in the center a little bit. So this shape looks a little bit like this. The domain, this is continuously going this way. It's inching its way this way. And the right side is still inching its way that way. So we still have negative infinity to positive infinity for the domain. And the range, this is going, let me erase this. The range, if we look at the y-axis, it is still continuously going down from negative infinity. And we look at the topmost point, it's still going to positive infinity. Alright, so this concludes this lesson on section 4.4, polynomials. Until the next time.